putting my camera in one spot to record half, and then move it halfway through, and then just finish up over here. Just keep erasing over here and be filling up. Make sense? That way it's closer and easier to read what I do. You can try to catch up on what we did. Roughly? Yeah, I'll roughly catch up on what we did, and I'll upload it on YouTube. And you can watch as fast as you want.
Okay.
Done. Enjoy. So that's how you get roughly caught up. You cruise through it.
Is last week's lecture not uploaded?
It is. I literally had it upload the next day, specifically
Yeah.
for Jacob and James to make sure it was up.
Yeah, so you should.
So let's begin today. And today's going to be a bunch of going over what we rushed through at the end last time. So at the end last time I said we're just going to go through sets real quick in a high level way. I gave you just definitions for what things were, playing around with them. So now we're going to go through it the way the book did. And then I found some teacher's class notes that I like that goes through sets axiomatically. So next time I might do that, and then we'll continue with this book, or we'll just continue with the book doing relations. I haven't decided yet. So we might recover all this stuff again axiomatically. So you remember last time I was complaining about the author because he says he's going to develop set theory intuitively rather than rigorously from axioms. And he says part of his justification was, well, we developed arithmetic axiomatically. Let's give you some contrast. And another part of his excuse was,
It gets covered everywhere else.
You're already very familiar with arithmetic, most likely, and you're not familiar with this stuff, so maybe doing this rigorously through, you'd get lost in the details type arguments. And then, yeah, he also tries to excuse it by saying other people always do it axiomatically, which currently is not the case, so, but this is a very old textbook, so when he was writing it, it must have been the common way to do it. Anyways, so I'll have to decide if I'm going to do the axiomatic way next time. Is that what you guys would prefer, or do you just want to keep going on to relations?
Prefer the axiomatic way, seeing how that's kind of why we took the class.
There's one.
I wasn't here last time, so I don't know what it looked like.
Well, it's going to look like this, basically, where we just cover. Maybe we'll have the conversation at the end of this, and we can decide if we just want to move on or go through it again axiomatically. Okay, so sets. We can't define what a set is, and because in our axioms, a set would be the domain of things that we're operating on. So our axioms are going to encode what a set is, and then, well, we'll leave it at that for now. So when we say what a set is here, it's just to give you some high-level intuition. That's what we're going to do. We're going to develop set theory intuitively. We're just going to appeal to intuition. We're, for a bunch of these things, not going to have rigorous definitions. So what is a set? A set is any kind of collection of any kind of entities. Any collection of anything, we're going to call that a set. There's nothing that you can't have a collection of that wouldn't classify as a set. So all people, all Americans, that's a set. All the integers, that's a set. All the chairs in this room, that's a set. Every red object in the universe, that's a set. Any collection of any entities, we're going to call it a set. Okay?
What about the empty set?
The set that doesn't have anything in it, the collection of nothing, yeah, the collection of nothing is going to be an empty set. And it's going to also be a set. So we don't require that there has to be anything in there, but anything can be in there. And we're going to call it a set. And we'll have that conversation if we do it the axiomatic way. Okay, so, and there's a couple example of sets. Now, the first thing we want to find is membership in the set. So we use this little epsilon symbol for membership. We would read this X in A, or X is a member of A, or X belongs to A. So X in A says X is a member of A. it's understood that the right-hand side thing here is always a set. If I have X in A is always going to be a set. And X is a member of that set. So that's one of the objects in there. So Jacob is in the set of all Americans. Good? Okay. So a couple examples. Elizabeth II belongs to the class. Oh, I didn't specify that up here. So sometimes, just for the sake of switching between our language, sometimes it helps to not keep saying set over and over again, to kind of help you almost put brackets in your mind on the sentences that you're talking about. Sometimes we also refer to a set as a class. So set, class, same thing. And might accidentally go back and forth between that kind of language. Okay, so Elizabeth II belongs to the class of all women. What does that mean? That means Elizabeth II is a member of, belongs to, the class of all women. This is a set, this is an object in the set, that's specifying it's an object in the set. Good? No? Okay. Next, set equality. So we say that set A is equal to set B, if and only if, for every x where x is a member of A, then x is a member of B, and if x is a member of B, then x is a member of A. So x is a member of A implies x is a member of B, and x is a member of B implies x is a member of A. You remember what the back and forth arrow is? If and only if?
Mm-hmm.
Anyone confused by this definition here? Nothing weird about it? Okay, so now with set equality, we can do a quick proof that there's only one empty set. This is going to be similar to our proofs for things like there's only one 0 element or one 1 element. Can't really use that. Okay, so the way we start this is, what do you think? How would we prove that there's only one empty set?
That there exists a set that
By way of contradiction.
is
By way of contradiction. So assume that I have two sets that are the empty set that aren't equal.
right.
Okay? So assume that there exists, what should we call them? A1 and A2 such that A1 and A2 are empty, and A1 is not equal to A2. Now we're going to show that A1 is equal to A2. Right? And that's going to be our contradiction.
Yeah.
Understand where we're going? So, what do we have? Then, for all x, x is in A1 implies x is in A2. Is that true?
Yes.
Do I know that x is in A1, x is in A2?
Yes.
How do I know that?
Because that's
X
what
is
equality
not
means.
A1. It's false.
It's one
We're
indicator.
proving it's equal. What's that? What'd you say?
X is not an A1, so it's a false statement.
Yeah, this part's always false. The antecedent of this implication is always false. X in A1, A1's empty. Nothing is in A1. X in A1 is always false. For every X,
Oh.
this is false.
Right.
So false implies anything is
True.
true. So for all X, this is the case. Right?
Mm-hmm.
Okay.
So I don't know how else to say that. 3, also, for all x, x in A2 implies x is in A1,
So that's true also.
right? So therefore, everything that's a member of A1 is a member of A2, and everything that's a member of A2 is a member of A1, therefore A1 is equal to
I
A2.
was like, where's the contradiction? But that is the contradiction.
Therefore, A1 is equal to A2. Contradiction. And we're done. Make sense?
Makes pennies.
Anything weird in the proof?
No.
Good? Okay, so now that we proved that there is only one empty set, we can
Make it set.
define it.
Yeah.
Right? The same way that we want to define like negative x.
Right.
Remember we had to prove that there was one and only one
Right.
negative x before we could define it. Okay. So now we can say what the empty set is. We'll call that one and only set, this thing, the empty set. And what is it? It's the set A such that for all x, x in A is not true. That's what the set is. It's the empty set. So there's nothing in it. Now, some quick notation to help us along our way. Not a member of is exactly what we mean by not x in A. X is not a member of A is logically equivalent to not x in A. Good with this notation? Okay, more notation. So, we knew how to describe some sets. We said the set of all men, the set of all women, the set of all integers, blah, blah, blah. That's one way we can describe it. Another way that we can describe a set is to just enumerate every element that's in the set. Just specify what's in the set. So when we want to specify a set that way, how do we do it? We do curly brace, comma, separate all the objects that we're saying are in the set, and curly brace. Make sense? So this is a set of King Kong and George Washington. Now you can have anything in a set, so here's another set. What does it have? It has 1, 2, 3, square, Bob. Collection of anything, doesn't matter. Sure, SpongeBob.
Square Bob.
Square Bob.
That's what you're leading us to.
Okay, so some things to note based off of our definition of set equality. Remember, A is equal to B if every element of A is an element of B, and every element of B is an element of A. Right? That's our definition for set equality. So, based off of that definition, the set 1, 2, 3 is equal to the set 3, 2, 1. Everything in this set is in this set, and everything in this set is in this set. Therefore, they're equal. Similarly, this set is equal to this set. Everything in this set is in this set, everything in this set is in this set. You might say, whoa, this one has 2 1s, this only has 1 1. So, pick any object in here, 1. Is it in here? Yep. Pick any object in here, 1. Is it in here? Yep. Yeah, but it's in there twice. Who cares? Is it in there? Yep. So it works. It satisfies the definition of equality. Good? So sometimes what we say, well, I shouldn't say we as in the math community. In computer science, the way we talk about a set is we say it's an unordered, unique collection to capture this exact idea. What we mean by that is we mean the order in sets doesn't matter, doesn't change the set, and duplicates in sets don't matter. In other words, every element in there is a unique element. Okay, and then one more thing to keep in mind, which you'll probably get confused by if you go on and do, those of you doing discrete math, this will probably come back to bite you a little bit, is that sets can be members of sets. There's no problem having sets with sets in them. There's no problem having sets of sets of sets of sets of sets. Okay? You can put anything you want inside a set, including other sets. Perfectly valid. So, the set 1, 2 is a member of the set containing, I'm missing one. Well, let's just say, what are the members of this set right here? The members of this set are, there's 3 members. They are the set containing 1, 2, the set containing 2, 3, and the set containing 1, 2, 3. These are the 3 members of this outer set. One of the members of this set is the set containing 1, 2. That's the member right there. Make sense?
Mm-hmm.
Okay. What about if I were to have something like 2 is a member of this set? Yeah, because it shows up 3 times, right?
No.
No, those are.
No, 2 is nowhere in this set. Is this 2? No, move to the next object. Is this 2? No, move